quasi-isometry invariants. Okay, so the first one that we saw yesterday was being finitely presented. Then we discussed volume growth. And so today I would like to speak about ends of topological spaces. So the first one was definitely an algebraic property. The second one, we were working on Kelly graphs, so then it was a little it was geometric in some sense, and here it's more topological aspect of an invariant. So this gives you, and it's related to the volume growth in some sense, but it gives you a different sort of information. So the end of a topological space supposed to tell you, to describe a way of going to infinity. Okay, so the setting that I would like to use, so it's not the most general setting, but I think it's good enough when we're dealing with groups and Kelly graphs. I will assume that X is a proper geodesic metric space. Okay. So let me remind you that a proper means that the compact sets are exactly given by their distance. Okay. Okay. So then, so maybe I should. How should I proceed? So the idea, for instance, if I have. So let me just make a small drawing. So, so what I want to understand is how to go to infinity. What are there qualitative difference of going to infinity? So here I've drawn something with three sort of funnels going out, and so the number, the ends of the space should describe how we will move out. So here in this case, before I give a rigorous definition, it will just mean that there is three different ways of going to infinity, because I can go either this way, or I can go up, or I can go down below. So now I have to find a way of expressing this idea of having different ways of going to infinity. And so for this, if you don't mind, I will change screens. I don't know what. Okay. So let me. So what we are going to do is that. So we have X. So for any compact set. Join and okay. Will be is defined by a collection of connected, open sets. So these sets are parameterized. So I name them U sub k or W sub k, maybe W I prefer. W sub k, where k is a compact set of x. So the property is the following, such that each Wk is an unbounded connected component of the complement of k, and the main property is that if you have W1, Wk1, and given Wk1, Wk2, there exists a compact set K such that the open set Wk is included in the intersection of the two. Okay, so let me redo my drawing to explain a little bit what this means. So this is my space X. So for instance, I want to say that I'm going this way. Okay, like I said before. So you pick a compact set. So for instance, I can take this one. So this is K1. And so then the unbounded component that I should consider is this one, Wk1. Okay? But of course, I could have holes here. Huh? So this one in the middle, it's a bounded component, so I don't care about. Now I could pick another component, so another compact set. So for instance, it could be something like this. In this, so let's say that this is K2. And maybe K2 is not connected, by the way. So it could be something like that. Okay, so this is also K2. And then in this case, what will be Wk2 that I have to consider? It will be this part. Okay. So this will be Wk2. And now my assumption, my second condition saying that given any two open sets, I need to find a third one that will be included in the two. So for instance, what I can pick is, let's do it in blue. I can take as a compact set this line. So this will be my K, and the Wk will just be like that. Okay? So in this way, I can express the fact that I'm going to infinity on one way or another way. Okay, so for instance, if I look at the real line, what you see is that I have exactly two ends because each time I will pick a compact set. It will be essentially contained in some interval. Then I can go either on the right or on the left. Okay? So this definition is a little complicated, I agree. But what is interesting with this definition is that it contains a lot of information. But usually, this is an observation, is that to define an end, it is enough to fix an exhaustion of your space by compact sets. Okay, so what is that? It is a sequence Kn of compact sets of your space, such that the interior, no, not the interior, I mean, okay, Kn is included in the interior of the next one. So it is an increasing sequence. And then the union of all the Kn is the whole space X. So each time you fix, where can I write? I should not have made this drawing. So each time you fix a sequence like that, Kn, you pick UN, connected component of the complement in such a way that you get a decreasing collection. So maybe I should stick to my W's. So you have a sequence of Wn that is decreasing, and this will define an end. So if I go back to my drawing here, maybe I'll just do a new one just there. So we can take balls, for instance, of radius n as the exhaustion. That's why I picked a compact set. And so what you can look at is that the sequence like this, so I will increase. So here you see each time you have a finite collection of sets that increase like that, and the complements will give you a decreasing sequence if you go up north or southwest or southeast. And each time you have this, it's enough to define an end, because each time you will pick another compact set, you won't have any choice because of the second condition that defines the notion of ends. So in practice, we define ends, we look at ends by looking at exhaustions, by fixing one exhaustion of compact sets. But when we want to prove something, it's much more convenient, usually, to work with this definition that is a little complicated. So do you have any questions at this stage? Or the definition is clear? Yes? So in this case, I will switch boards. And so what we are interested is our interest lies in the number of ends. Of the space. Okay. So maybe the first proposition that I will just sketch. Maybe another remark before I proceed. Sorry. Remark. So here I've defined an end for proper geodesic metric spaces. Actually, an end, to define an end, it is enough to work with X to be locally compact, connected, locally connected. So to be locally connected is very interesting because it means that the connected components of open sets are always open, and you need that to get local connectedness. And also second countable. So second countable means that you have an exhaustion, like I defined before. And you only need these properties to define ends, but but since we are going to apply it for Kelly graphs, and we can always apply for Kelly graphs, so these are already metric spaces that are proper and geodesic. So it's fine. So the first thing, if we want to consider the number of ends for a group, is suppose that it is a quasi-isometric invariant. So if phi from x to y is a quasi-isometry between two proper geodesic metric spaces, then what do I want to say is that then x and y have the same number of ends. Okay. So how can we prove that? So I will just sketch the proof. So we will consider psi to be a quasi-inverse of phi. So let me remind you that this means that the distance between the composition phi composed with psi with respect to the identity for the submetric. And also, if you go the other way around, this is bounded by constant c, and both phi and psi are lambda c quasi-isometries for some constant lambda and c. Okay? And so the idea is the following. So in x, so here you have x, and there you have y. So you pick an end. So what I want to prove is that the map phi and psi will actually map. There will be a canonical way of assigning an end to the image of an end will be an end. So that's what I want to get to. So I consider an unbounded open set given by so this is some w, wn, and then I have some wn plus 1. And so now I apply my map phi. And so on the other side, what I will obtain, so since phi is not a continuous map, it will be something that can have holes, but it is an unbounded set. So this is phi of wn. So what I want to do is to make it to associate an unbounded connected set. So for this, what we do is we consider wn hat. It will be the 2C neighborhood, open neighborhood of phi of wn. And in this case, oops, now this becomes open and connected. And so if your sequence of WNs are far enough, then you will find there exists a subsequence NK such that these WNK hats define, or this sequence defines an end in Y. Okay, so the idea is that the image of a connected open unbounded set, is a set that is unbounded, but a quasi-isometry does not preserve the fact to be connected, nor to be exactly the boundary of a connected component of the compact set. So what we do is that we increase it a little bit, and this will define us a new way of having n. So we have to take a subsequence just to make sure that the next one will be far enough away from the boundary of the previous ones. And so how do we prove that this is really an association of mapping an n to an n? Well, we consider the inverse. And by taking the quasi-inverse, what we're trying to show is that it will give us a sequence that will be that will define the same n as we started from. So this will be psi of some w hat n k. Okay. And so in this way, what we see is that we have a bijection between the number of n's. Okay. Is it convincing enough? Yes? Any questions? So this is just a sketch. So the idea is to show that when you have a quasi-isometry, there's a natural way of mapping an n to another n by this little procedure of thickening the image inside the next. So if there are no, so I cannot see what's going on with this thing, so maybe I switch. So if there are no questions, then I will state the main result concerning finitely generated groups using another board, if I can. Okay. So the main theorem, oops, sorry. Theorem. So let G be a finitely generated group. Then G has 0, 1, 2, or infinitely many n's. Moreover, G has no end, is equivalent for G to be finite. G has two ends if and only if there is a finite index subgroup isomorphic to the infinite cyclic group Z. Yes. Okay, so you see that the condition, so what does it mean? Huh? So maybe I should say that, saying that a group I don't know what I wrote, a group group G, I don't know what's going on. Okay, yeah. Group G has n ends means that any locally finite KV graphs of G has n ends. Okay, so this is well defined because the number of ends is quasi-isometry invariant. Okay, so what I would like to do is explain a little bit how the proof goes on, how it works. So the proof is rather amusing. So let me, maybe first I will give some examples. So of course, for a finite group, there are no unbounded components. So the number of ends is 0, and I don't want to talk about that. In the case of Z, what you see is that you have exactly 2 ends like the real line, because you can have one of the telegraphs is just the line, and we saw that it had 2 ends. If you look at Z2, then in this case, if you take the standard generating set, so then you have the grid, and you can prove that it is one-ended. And if you take any free group, for example, the free group on 2 generators, then you have infinitely many ends, because you see you have a tree, and in the tree, each time you cut very far away, then you increase the number of connected components each time, because it goes infinitely far. Okay. And so you see that all cases appear at least. Okay. So now I would like to give an idea of why there cannot be 3, a group cannot have 3 or 4 ends. Okay, so stage. So let's assume that we have, for instance, n ends, so let G be with n ends, and I assume that n is at least 2. So I will make a drawing like that. Know that I have a compact set, because it has finitely many ends. I can find a compact set that is big enough so that there are exactly n connected components that are unbounded. So I will call them maybe not this correct. Okay, B1, B2, W1, W2. And here I call it Wn. Okay, and what I want to prove is that actually n is equal to 2. It's a little weird, and so first, so this is the Kelly graph. I fixed one Kelly graph on my group G. So what could be done? So first, I have infinitely many elements in my group, and my compact set K is contains only finitely many vertices, so elements of the group. So then this means that I can find an element of my group G that will shift K out of itself. So for instance, it's just a matter of labeling correctly the unbounded components. I can assume that the image of some element G will move my set K into Wn. So this will be G of K. Okay. And so now I consider L to be K union G of K. So this is a compact set, and I want to look at its unbounded connected components of its complement. So of course, what I see is that all the ones that are on the left, W1 up to Wn minus 1. Okay, so here actually, instead of saying that it is W2, I should have called it Wn minus 1. Oops, minus 1, sorry. Okay. And so I want to count that I have at least all the ones that are disjoint from Wn. So this means that I have W1 up to Wn minus 1. And then in Wn, I know this component is bounded. G of k is a compact set because my group acts by isometries. So in particular, it is continuous. And so I have at least one end in that is contained in Wn. And since I know that I have exactly n ends, so I have just another one that I will name W hat n that is contained in W1. Okay? So this means that when I look at these two, at my set L, I know exactly how many unbounded components I can have. Now the thing is that if I look at G of k, if I look at the complement of G of k, I know that I have exactly n connected components as well because G acts by a homeomorphism on my space. Okay, so I have, of course, W hat n because it's attached to the boundary is attached to G of k, and then I have n minus 1 ends on the left. But on the left, you see that k union all the Wj from j equals 1 to n minus 1, this is connected. Right? So this means that I have only one unbounded connected component there. So if I call this W prime. So this is just Wn union W prime. And I know that this is exactly, so here I've given you the number of ends of unbounded connected components of the complement of k, of G of k. So this implies that n has to be equal to 2. Okay? So that's the sketch of the proof. So the idea was to show that by shifting k and by using the fact that it has to be a maximal, that I know that I have the maximal number of n's, actually I cannot have more than 2. Okay, so then the picture is the following. Your space is like a strip. And here you have k. And then you have G of k. That's just on the right. So here I have W2. And here I have just W1. Okay? And now I would just like to, so I'm already out of time, but I would just like to say why, to give a sketch of why my group G has a finite index subgroup that is cyclic. So what I claim is that the subgroup G generated by G is cyclic and has finite index. Is infinite cyclic, I mean, and has finite index in my whole group G. So the idea is the following. So to prove that G is cyclic, it's easy because you see that G shifts K disjoint from itself. So then it's impossible that the power of G will come back because you go always further off. You see, each time for every n positive, what you will have is that G iterated n times of W2 will be strictly contained in W2. So this means that you cannot have finite, G cannot have finite order. So this means that the group generated by G is indeed infinite cyclic. Now, how to prove that G has finite index, that this group has finite index in the whole group G? Well, the idea comes from what I want to prove is that the action of G on my space X is geometric. So the action of G on the K graph is geometric. And if I can prove this, the fact of being co-compact will tell me that actually the quotient will be finite. So what I really want to prove is that the action is co-compact. I already know that the action is by isometry, that it is properly discontinuous because it's a subgroup of a group that already acts properly discontinuously. So the only thing I need to get is to say that I have a compact fundamental domain, because this means that this compact fundamental domain will contain finitely many elements of my G, and this will be a set of representatives of the quotient. So how do we do that? Well, we have to pick have a candidate for the fundamental domain, and here it will be what's contained between K and G of K. So the idea is to prove that any point can be mapped into this set here. So this set, what is it? It is G of W1 intersected with W2 union K. Okay, for instance. Or K is maybe already, I don't need K, I guess, but this is enough. And so if you can prove that any point has to go through this set, then you're done. And why is it the case? It's because everything is pushed under G towards the end of W2 at infinity. Okay, so I think I will stop there.